Hey everybody. So today we're going to be talking about the Milky Way, our own galaxy. And you may be surprised, a lot of people are surprised, that our Milky Way galaxy, our galaxy, is the one that we know the least about of all the galaxies out there. Well, the reason for that is simply because we're inside it. When you're inside it, it's hard to see the big picture as to what's going around. So a lot of what we've learned about galaxies actually comes from looking at other galaxies, and we've had to use some kind of clever tricks to figure out where we are in our own galaxy, as well as where all the different structure, the spiral arms and things like that are. So that's what we're going to be talking about today. Let's get started. Okay, everybody, so as I said, we're going to be working with the Milky Way, so make sure you've got the Tool 24 out. Looks like this. Lots of pretty pictures for that one. And pause the video until you're ready to go. All right, so as I said, we are actually inside the Milky Way galaxy. And so seeing what its structure is actually kind of difficult. We didn't know for a long time if we were in a spiral galaxy or some other type. In fact, until about 1920 or so, we thought that all the stars we see, our galaxy, was the entire universe. We didn't realize that there were other galaxies outside of our own. So it's only been in the past 100 years or so that we've made that realization. The picture that you're looking at now is the Milky Way, and you probably have seen something at least similar to this if you've ever been outside, out away from the city lights and things, but it probably wasn't quite this intense. What they've done is they've put their camera on a tripod and they're following the sky, and they've just left the shutter open. So this is just a regular camera, but it is on a motorized tripod so that they could take, a 10-minute exposure. That's the only way you're going to get the kind of dramatic pictures that you see here. The galaxy got its name because to the naked eye, all the light from these stars, this is billions and billions of stars, just kind of blends together and makes it look kind of milky. And you can see the Milky Way from every point on Earth because, well, we're inside it. And so, if you go around to the southern hemisphere, you see a different part of the Milky Way depending upon which way we're looking out of the disk. And even here though, you can see that this is the bulge of the Milky Way, and then it kind of tapers off to a disk. Just keep in mind that that goes all the way around us. This area that you see in here, these are dust clouds that are in between us and the main center part of the Milky Way. Figuring out where we are in the Milky Way actually was a little bit of a challenge. And so what we did was we looked at what are called globular clusters. And a globular cluster is just an ancient collection of stars, anywhere from 50,000 to a million stars or so. And they're very ancient. They're pretty much all red stars is all that's left because all the blue stars have died off. But they orbit the center of the galaxy in all directions rather than lying in the disk. And so what we can do is we can figure out the direction and the distance and then plot those relative to Earth. So here's the sun, and then we just calculated the distance using Cepheid variables that we learned about last week. So we figured out the direction, the distance to this one and this one and this one. The center of this distribution, remember they were all plotted from the sun, but the center of the resulting distribution must be the center of the galaxy. And so that's how we know that we're about 8,000 parsecs, 8 kiloparsecs away from the edge. Each edge from the center outward is about 15,000 parsecs. So we're a little over halfway between the center and the edge of the galaxy. But this is the calculation that enabled us to determine that. Now for the spiral arms, obviously you can't see the spiral arms from when we're inside. If you go back to that original picture here, you're not going to see the spiral arms. So are we even in a spiral? Well, the way we can tell is by looking at radio emission, because those gas clouds are putting out, they're emitting radio waves because of the molecules. We talked about that in the section on ISM. So by looking at the radio waves then, I can see where these particular things are by looking at their redshift and their blue shift. Now, the reason they're going to have different velocities is because of Kepler's law. Kepler's third law says these that are enclosed are going to be spinning faster than these that are out here. So when I look at the gas, the ones that are, if this is where the line is supposed to be, this from spiral arm 1 here is going to be blue shifted just a little bit because it's not that far out, whereas this one is going to be, or red shifted, and this one's going to be shifted a little bit further. So by looking at it is the blue shift. Looking at the blue shift in this case, then you're able to see this one's moving faster, therefore it must be farther out. And we don't see anything with a blue shift in between these parts. That's how we know that this is just mostly empty space. So this then is that first arm, and this is the second arm. Now there's a problem with this. Kepler's laws say these things should be orbiting, and the inner parts should be orbiting faster than the outer parts. Well, if that's true, then these spiral arms are going to get wound up tighter and tighter and tighter. Eventually, you're just going to have a disk. You're not going to have any spiral structure at all. Well, and in fact, it turns out that it doesn't take very long for that to happen. Maybe, 500-600 million years or so. Well, the galaxy is 14 billion years old almost. So how is it that we have spiral arms? So this was a pretty serious problem. And the best model that we have for that, and this is shown on the back page that you have here, is that there are density waves moving through the galaxy. So moving around the galaxy like this are density waves. And density waves are just areas where we've got compressed matter. And it's kind of like a traffic jam. So if you think about, if you're in a traffic jam at the Deck Park Tunnel or something like that, the traffic jam stays in the same spot, but the individual cars that make up that traffic jam won't be staying in the same spot. So they move in, they slow down, they move out. So we think the same thing is happening with these stars. You've got a density wave, and the stars themselves move faster than the density wave, as Kepler's law says they should. But as they move, as the gas and dust moves into this area, it gets compressed and it triggers star formation. And so most of it's going to produce O stars, it's going to produce B stars, it's going to produce G stars, it's going to produce M stars. Now think about it. Which is going to live longer, the M stars or the O stars? The M stars live longer. So they live long enough to just keep on moving. And they may, continue on into the next spiral arm, because there'll be another density wave out here. These O-type stars, though, they only live for 10 million years. They're not going to make it very far. So once they move, they don't move very far before they become a supernova and they die. So this is why our spiral arms are blue, because this is where the blue stars are. Now that does not mean that there are no red stars. The red stars are there, but think about which one's brighter. Those blue stars, O stars, are much, much more luminous. They're drowning out those red stars, so you don't see them at all. In between, those red stars are faint. So there are red stars in between the spiral arms. You just can't really see them because they're so dim. So this is why those blue spiral arms tell us that there must be active, ongoing star formation happening, because the O-type stars, the blue stars, simply don't live for very long. So it looks something like this. We get gas and dust that moves into the density wave. They form stars. Most of the really high mass O-type stars don't live very long. They explode, and so they push that gas outward. And so you see that the density wave slowly moves through. So the density wave is traveling much more slowly than the stars themselves. The stars themselves move into the density wave, into the traffic jam, out of the traffic jam. So they honor Kepler's third law, but it's the spiral arms themselves are due to these density waves that are moving much, much more slowly as they go around. Now, when we look at the different parts of the galaxy, when we look at the disk of the galaxy, our sun and most stars in the disk may start out, slightly above the disk, but keep in mind that there is not a single central object. We will talk about there is a black hole in the center of the galaxy, just spoiler alert, but everything is not orbiting that black hole. Everything in the galaxy is orbiting each other. And this is the fundamental difference between a galaxy and a thing like a star, things like a star system or things like that. The gravity of all of these stars are affecting all of the rest of the stars. So if I have a star that's, maybe up here, well, the gravity of the stars below it are pulling it down, and it's still going around the circle. As it goes down, then it's got some speed, so it overshoots. But now the gravity of these stars is above it, so it pulls it up like this. So it's almost like a merry-go-round. So our sun's path around the center of the galaxy is not a straight circle. It's like a merry-go-round as it goes up and down. But in general, those don't vary too far from the disk. So the disk does have some thickness, but not much compared to the width of the disk. So this is showing all of the different orbits coming in. So we've got circular orbits in the disk, but they're roughly in the same plane. That's this kind of merry-go-round motion, the yellow arrows that you see here. The halo, those are those globular clusters that we were talking about. Those are the green arrows that you see. And they're circular orbits, but they're in random inclinations, random directions, coming through in all different directions like that. Then the third part of the galaxy is called the bulge. And this is the area where we've got lots and lots of high density stars, lots of stars going around. And they are also in circular orbits in random inclination. So you can see that with the red arrows here. So in this way, we see that there are three main parts to the galaxy. There's a disk, there's a halo, and there's the bulge. So when we look at the structure of the Milky Way, and this of course is not the Milky Way because we'll never get a picture of the outside of the Milky Way, but this is another typical spiral galaxy, and you see we've got the bulge in the center, here's the disk, and then these stars, this is actually a globular cluster right here, these are orbiting around the entire galaxy, and that's what's making the halo from that. Now this is the bulge as seen from Earth. So when you're looking in this direction, you're looking towards the center of the galaxy. This actually occurs in the constellation Sagittarius. So when we look at Sagittarius, then this point right there is the center of the galaxy. Now, there's some special things going on, but I don't want you to lose sight of the fact that the gravity of the center of the galaxy is not what's making things go around. Lots of people get confused. They say, well, there's this massive black hole and everything's orbiting it. Well, no, they're orbiting each other. And so the galaxy has its shape just because that's the average orbits. And you think about it, if I've got a single star that's traveling around here, I'm only going to have one star here, but I also have a star on this side as well. And so overall, the galaxy looks solid, but it's really not. It's really composed of just these orbits of all these stars. Next lesson, when we start talking about different types of galaxies, that's going to be an important concept. So if I want to look at the galactic center, unfortunately, you see that there's a big dust cloud in between us and the galactic center. So we can't actually observe it in visible. Fortunately, you guys know visible is not by far the only type of light that we can receive. So we can actually look at it in a bunch of different kinds of light, and that allows us to probe all the way down into the center. So let's take a look. So this is looking at the center, and then this is in the same direction, although we've tilted the picture so that the dust clouds are going straight up and down. Right there is the center, the galactic center. So you see the bright part right there. That's this point down here that we're looking at. So this little square is what you see right here. So that's blowing up just this area. So most of what you're seeing here is gas and dust. This is, the scale bar here is telling you this is a distance of 200 light years. So now we're going to take that same picture then, and we're going to zoom in on an area that's 50 light years. So just about a quarter of this, so about this big right here. And so now we see this part, and we see that there's this structure with some gas and dust that seems to be spiraling down towards the center. Here's that same picture. And now we're going to look at 10 light years. So 10 light years is an area about this big, looking towards the center of it, which is actually over here. And so now you can see that we also still can see that material spiraling down, and there's some dense areas here that are putting out a lot of energy with that. So now we're getting into, I believe this is a gamma ray picture here. So this is 10 light years, so this is just 1 light year. So this is looking at just this very center part right here. So we've zoomed all the way down from here, zooming in closer and closer until now that point marked by the arrows, that is actually the center of our galaxy. And you see there's lots of stars in that area, and they're all orbiting this, but they don't seem to be orbiting anything. And so you can see these are the stars that are closest to the galactic center. This is an animation, it's not an actual photograph, but it's following them in 3D, and they're all orbiting this point right here, but there's no star there. So what we can do is we can use Kepler's third law to get the mass. You guys know how to do that. We studied that with the binary star. So we'll do it as a sample here in just a minute. But by looking at the semi-major axis and the orbital period, we can figure out the mass of what's in the galactic center. So let's do that. So this is a close-up picture of the two stars that are closest to orbiting the center of the galaxy. And that's the center is right here, right where my mouse is pointing. So this red dots here, that's the position of the star SO2. And this one is SO102. So let's look at star SO2 right here. We only need to look at one of them. We can measure the semi-major axis. You measure the entire major axis and just divide that by 2. And we find that the semi-major axis is about 970 AU. The orbital period, the time it takes to go one time around, is a little over 16 years. So let's calculate the mass of that central object. So we're going to need Kepler's third law when we're going to find the mass. So A, the semi-major axis, is 970 AU. P, the orbital period, is 16.05 years. Here's Kepler's third law. This is exactly what we did with the binary star system. So we take 970, and I'll put this in my calculator. You do it with me. So pause if you need to get your calculator out. So we go 970, and that's going to be cubed. So I hit y to the x and 3. And I get 9.13 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. 9.13 times 10 to the 8th. And I'm going to divide that by 16.05 and hit the x squared button, which is 257.6. And I get a total mass of about 3.5 million solar masses. So that's what I'm getting. So this is an object that is 3.5 million solar masses. And yet it's so small, it fits into the intersection of the orbit of these two stars. And it's putting out no energy whatsoever that we can tell. So the only thing that this possibly could be is a supermassive black hole. And so this is an X-ray picture. Periodically we get X-ray flares. What's happening is, we talked about how, when this pen falls, it's giving up gravitational potential energy. It's turning it into thermal energy. Well, here it's giving up so much gravitational energy that instead of emitting infrared, it's emitting X-rays. And so every time a star or some gas or whatever spirals down into this black hole, it goes faster and faster and faster until just before it crosses the event horizon there, and then it emits those X-rays. So the only object that we know of is a supermassive black hole that can be that massive, that small, and have those kind of flares. All right, so that's it for the Milky Way. In the next lesson, then, we'll talk about some of the galaxies. So the galaxies that we'll be talking about, some will be spirals like our own, some will be two other different types. An elliptical galaxy kind of looks like a football-shaped collection of stars, and then an irregular galaxy which has no structure whatsoever. So we're going to learn the different characteristics of these galaxies by applying what you've learned when it comes to stellar evolution. That's what's determining their color and all that sort of thing going on. So we're going to find that each galaxy can have 100 billion stars, but there are 100 billion galaxies or more out there. So space is not just big, it's oh my god big. We'll see you next time.